Let me show you a number of interactions that we have between two trolleys initially of the same mass, moving along a track here. There is some friction on the track, but it's relatively small. So I'm going to make the assumption that while they're moving along the track, there are no external forces. There are forces between the trolleys, but we can say that the total momentum of the system is always conserved. Now let me show you a few of these. Here's the first one. This is an elastic interaction. I've arranged it such that there are magnets in these trolleys, so rather than actually colliding with each other, they actually interact smoothly with each other. I can change the mass of one of them and get a slightly different behaviour. But there's an interesting idea on this one here. The way that we would define this is that the total kinetic energy of the system on an elastic interaction is always conserved. If you use those two rules, the fact that the kinetic energy is conserved and the momentum is conserved, you can actually come up with another conclusion, and you can show that in any system, whether one is stationary or not, the relative approach velocity is always the relative separation velocity. Again, I can change the masses of the objects, and that is always true. So that's what we call an elastic interaction. The second one I want to show you is something that's more common, an inelastic interaction. This time I've moved it so that one of the magnets is not facing the other trolley, and I get that sort of behaviour there. Now you can clearly hear that there is some of the energy being lost there, and you can also see that this time, rather than one of them ending up as being stationary, that they both move. So again, for an inelastic collision, we find that the total momentum is conserved. However, the kinetic energy is not conserved. Some kinetic energy is lost. And that's what we mean by an inelastic collision. There's a third type of collision that I want to talk about, and this is called the completely inelastic collision. Let me demonstrate that with this one here. If you get that sort of behaviour, again, I've arranged the trolleys such that there is some Velcro, so this time they actually stick together. A completely inelastic collision is where the two objects stick together. Again, there are no external forces, so the total momentum is conserved, but this time here, again, we can say that the kinetic energy is reduced. There is less kinetic energy there. So again, the relative approach velocity will, in that case, be always greater than the separation velocity. Final example I just want to show you here is something that we call an explosion. There's a plunger in there, and when I hit the top of that, that will release some of the potential energy. So this would be what we call an explosion. Obviously, what we can see is going on there, that the separation velocity now is greater than the approach velocity, and the kinetic energy obviously increases because some of the potential energy that was stored in the spring has been released and converted into kinetic energy. Now on this particular arrangement, they are stationary, there's no approach velocity, but I could have an arrangement where that plunger could be released when the two objects collide. So I could, if I got a different trolley, get something where the trolleys come together, they collide, it releases the energy, and again the separation velocity will be greater than the approach velocity. So just a quick summary on all those cases: inelastic, elastic, or an explosion. Because we're assuming that there are no external forces, the momentum is always conserved. Okay.